Okay, so welcome to the 22nd video in the Discrete structure series, and this video is going to resume our discussion of our last video from propositional logic, and we're going to continue with a look at tautology, contradiction and contingencies, then the idea of logical equivalences. We'll see some truth table examples. Then we're going to have a look at some special logical equivalences or identities, and we're going to close the video with a look into the idea of satisfiability. Okay, with that overview, let's get started with our first topic of tautologies. So tautology is essentially a statement that is always true. A proposition that is always true is called a tautology. And I want to remove one confusion from this definition. So we discussed that the proposition is something that will immediately be resolved as a true or false, right? So when we say always true here, we're just saying that it is true no matter what its inputs are. Okay, so let me say I will go to class or I won't. This sentence is a tautology because regardless of whether I go to class or I don't, I am bound to satisfy this or criteria. So in that context, we are not saying that this entire sentence is sometimes true and sometimes false. If you look into this statement, going into class is an input to this statement that can either be true or false. And when we say always true, we mean that no matter if this is true or false, the resulting statement on totality will always be true. So in terms of propositional symbols, any proposition that says P or not P is a tautology. And the way to check if a given proposition is a tautology, we need to draw its truth table and we want to make sure that all values are 1 for our given expression. So for example, we are given P or not P. Let me show you what the truth table would look like. First, I recognize my variables. I only have P. And so the two values for P can either be false or true. And in order to calculate this expression, let me calculate not P. And then on another step, I can do P or not P. So not P will be calculated just by inverting these values. So false will become true and true will become false. And here I'm taking an OR operation and I can see at least one of these two values are true. So these will both be true. So you can see no matter what truth values we use for our composing propositions, this expression always results into a true. And therefore this is a tautology. So you might be given a compound proposition like this and asked to prove if it is a tautology. And you could always expect more than one variables. I only have P here, but you already know how to draw truth tables for more than one variable. So you can draw the truth table and show that all the values in the associated column are true. We are going to be drawing 3 variable truth tables in the later section of our video. So I'll just leave the discussion of tautology and move into contradictions. So we won't need to spend much time on this. This is the exact opposite of a tautology, and a contradiction is a proposition that is always false. And just for some rigor, I added this part, no matter the truth values for its composing propositions. And this could be added to the definition of tautology too. So let's see a similar but very easy example, P and not P. So it is easy to see in this statement that one of P or not P is bound to be false. If P is true, not P will be false. And if not P is true, P will be false. That means when I'm taking an AND operation, one of the two values are bound to be false. And therefore the resulting AND would always be false, no matter what values I choose for P. Therefore this expression is a contradiction. So the definition is not much important here, but you really want to be able to show that some expression is a contradiction. So let's say you are given a compound proposition and asked to prove that it is a contradiction. You want to be able to draw the respective truth table and show in the associated column that all values are false. So exactly the same thing that we did with tautologies, but this time we want to ensure all values are false. Okay, so let me trust your ability to draw truth tables and move on to our next topic of contingencies. So this is also just a matter of definition. A contingency is a proposition that may sometimes be true or sometimes it may be false depending on the values of its composing propositions. For example, let me write anything random. If I write P or Q, this is a contingent expression and it is a contingency because its value depends on the values for P and Q. And I'll stress again, contingencies are just a matter of definition. You should focus much more on tautologies and contradictions because they are extremely relevant in proof methods. And you'll only be asked questions about verifying if something is a tautology or a contradiction. It's rarely asked to verify that something is a contingency. Okay, with that said, let's move on to the next topic. We're going to see the idea of logical equivalence. Two or more propositions are said to be logically equivalent if they always have the same truth values. Okay, so in the previous topic, we looked at one proposition and we wanted to see if they were true for all inputs, that would make them a tautology, or if they were false for all inputs, and that would make them a contradiction. But here we are not looking at one, but more than one proposition, and then we are varying the inputs. And this is not about having all true or false values, but making sure that all values correspond. So for one set of inputs, all propositions should evaluate the same truth value, either true or false. And if we can ensure that for all inputs that is the case, that for all inputs, these values are exactly the same across the rows, we can conclude that the behavior of these three propositions are equivalent because they are responding similarly to similar inputs. So let's see a proper example to demonstrate this. I want to prove the distribution of OR over AND. So let me write this expression. So it is asking me to prove this expression is logically equivalent to this one. So let's begin with our truth table. On the left side, we'll list our inputs, and on the right side, we'll list our outputs. By looking at either of the expression, I can tell that I have three inputs, P, Q, and R. So let me list them here. And then I start breaking down which expressions I need to evaluate based on the precedence. So for example, here the bracket is put with the AND. So this is what I need to calculate first, Q and R. So let me make that into a column. Once I have this, I can simply OR it with P. And this column is going to generate truth values for the left hand side. And I see that I need three more columns, P or Q. I need P or R. And I need a column that ANDs these two. That would be P or Q and P or R. And you know, this is just binary counting in 3 digits. I want to use T and F though. Let me just fill this quickly. So I counted from binary from 000 to 111. But there is another trick. You could go alternate FT, 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 FT for this column. And then you'd go groups of 2. And then you can just do groups of 4. And if there's one more variable, you can just do groups of 8. And that's how it scales with more variables. But for us, this is enough. So let me start filling in these values. So I'm looking at Q and R. And I know it will only be true in here and here. So let me just put a false blindly for other spots. So in order to calculate this column, I need to do an OR between P and Q and R. So this is my Q and R column. I have P here. So this false and this false would result to a false. So would this. And let me just fill the remaining ones. Now let me also fill these two columns quickly. And finally, to obtain this column, I just want to do an AND between this and this column. So let me do that and fill the values here. Okay, my job of filling the truth table is now done. And now I want to compare the columns for the left and the right hand side, which is essentially this column compared to this one. And you can see all of the truth values in the corresponding rows are exactly the same. Okay, so you should write that conclusion. Upon observing the truth table for the left and right hand side, we can see that the truth values are same for all the given inputs. Therefore, we can conclude that the given statements are logically equivalent to each other. And before jumping into the next topic about logical identities, I just want to mention one thing. This notation is the same as this notation and it also signifies logical equivalence. And this is different compared to this. This is just a double implication and this is the symbol for logical equivalence. And one last point, the idea of logical equivalences can also be defined using implications. So we say that A is equivalent to B if A double implies B is a tautology. And this should be easy to see. We already defined this as a situation where A causes B and B causes A at the same time. And in our last lecture, we mentioned that either both A and B will happen at the same time or both will not happen. So if you guarantee that A double implies B is a tautology, you are kind of guaranteeing that both A and B will happen or both will not happen. And therefore, you are guaranteeing that they will have the same values in the truth tables. Because one being false should imply another being false and one being true should imply another being true. So just to make the earlier definition complete, you could say that P and Q are logically equivalent if they have the same truth values. And in other words, P double implies Q is a tautology. If you add that part, it will make it even more accurate. So the next topic that we're going to look at is going to be a list of logical identities. And these are compound propositions that are always true. So under logical identities, we'll just be looking at a set of equivalence relations. And these are really useful results that help us build new inferences and simplify logical expressions. So let us begin with identity laws. And the identity law is the same for all kinds of groups. Once you have an idea of a group, you'll see that the identity law is simply looking for an identity element. We looked at identity laws earlier in our course under sets and we found the identity elements under union and intersection. And here we're going to do the same thing. We're going to find identity element under and or. Okay, so given a proposition P, what can I AND this P with so that the result is P? And the answer is true. When I AND a true, no matter what P is, I'm still going to get a P. So I said true is the identity element under conjunction. Similarly, under disjunction, I have P or false equals P. It's logically equivalent to P. Since false does not contribute to an OR operation, whatever truth value P has will be translated over to the right hand side. And similar to set theory, we have two domination laws. And here the question is a little bit different. What can I AND P with so that it will dominate P and become the result itself? So I can AND with a false. If I AND with a false, no matter what value for P I choose, this false will dominate and become the result. We also have a domination law under disjunction. So if I do P or true, the true will dominate this OR operation and regardless of what P is, the result will always be a true. The next set of laws are called idempotent laws. And idempotent refers to a process that can be repeated any number of times without changing the result. So exactly same to the set, intersection and union, we have two idempotent laws here. P or P will be equal to P. And no matter how many times I keep ORing P with itself, the result is always going to stay P. So taking an OR with itself is an idempotent operation. You could do it 1,000 times, million times, and it would not affect the result. Similarly, there is an idempotent law under AND or conjunction, and that says the same thing. P and P will always be equal to P. Okay, then we have the double negation law. If you negate and then negate again, you get the original proposition. This should not take much explanation. So the next set of laws are the commutative laws, and you should understand the meaning of the word commute. It just means to interchange. So a commutative law would hold if I could interchange the rules of my propositions and still get an equivalent value. So can you say if OR is commutative? Well, can I change P and Q in order to get the same values? Yes, P or Q is the same as Q or P. Okay, so OR is commutative and so is AND. P and Q is also the same as Q and P. Okay, so these both expressions are commutative, and the commutative law holds for any number of variables. You could, for example, have 5 variables and each permutation of them would always result into the same value. Okay, next we have two associative laws, and we know this law is about groups or associations. So I would say that an associative law holds if I could make groups in the expression in any way, and any of those methods would give the same result. So let's say I'm considering P or Q or R. Okay, let me write the same thing here, P or Q or R, and let me make an association like this here and like this here. So here I'm calculating Q or R first, but here I'm calculating P or Q first, and my claim is that both processes will end up in the same result. And the associative law also holds under conjunction. If you are taking P and Q and R, you could do that in any order. And my bad here, these are equivalences. Alright, so moving on to the distributive set of laws. And under distributive laws, we always study the distribution of one operation over another. So we'll look at the distribution of AND over OR, and then we'll also look at the distribution of OR over AND. So let's say I need to distribute AND over OR. So let's say if I P and Q or R. Okay, so Q or R is here and I need to distribute this AND to the inside of this expression. So this is essentially equivalent to this expression. P and Q, I take AND with the first term. Now take the common operator OR and then take P and R. Okay, and I distributed this AND over this OR. Exactly the same way I could distribute OR over AND and also get an equivalent expression. So if I were to take P or Q and R, this would be equivalent to P or Q and P or R. So we can say that the AND can be distributed over OR and also the OR can be distributed over the AND. The next set of laws that we'll look at are really important. These are called De Morgan's laws, and the pattern in De Morgan's law is the same throughout all of mathematics. It basically talks about how to distribute complement over conjunctions and disjunctions. So if I have something like P and Q and then I take a complement like this, De Morgan's law suggests that the result would be obtained by taking complement of each term but then flipping the inner operator. If it is an AND, it will be changed into an OR. If it is an OR, it will be changed into an AND. So in this case I have an AND, so it will be changed into an OR. And this works for 3 variables and it also works for OR. So if I were to have P or Q or R and then take a complement of this, it would just result into P complement and Q complement and R complement. And it's also really important to know this, it works if these operators are not the same as well. So for example, if I were to have P or Q and R and then take the complement of this expression, I could follow exactly the same logic. Even though I have an OR and an AND here and these are different, I could apply the same logic and this would be equivalent to P complement, flip this will be an AND, Q complement, since this is an AND initially, this will be an OR and then R complement. Okay, you are allowed to do this. So when you remember the De Morgan's laws, remember that it complements each term and flips the operator. Okay, next we'll look at 2 laws under absorption laws. And this is also quite intuitive. Let's say I have this expression P or P and Q. Can I think of a way to simplify this? I can see that the value of this expression entirely depends on the value of P. Because if P is true, no matter what this expression is, this P will automatically make the expression true. And when P is false, this expression is automatically false regardless of the value of Q again. So no matter what value you choose for P, true or false, the value of this expression does not depend on the value of Q in both cases. And with a little more thought, you can also see that the resulting value is exactly P. So you can see that this Q kind of got absorbed by the P, and that is why we call this an absorption law. We have another one that works under conjunction as well. So if I were to take P and P or Q, it is also equivalent to P. I could always verify this with a truth table, mind you. So let me also show that. I always mention this, but don't actually draw the table. Let me do it this time. And you could see that these values are exactly the same as these values. So using a truth table, I'm able to verify this equivalence. And this will be true for all the laws that we discussed so far. So any of those laws might be chosen and you might be asked to verify its truth using a truth table in your exam. And all you want to do is to draw the necessary truth table, derive the left and right hand sides as separate columns, and ensure that they have the same truth values. So we're going to have a look at the next set of laws, and these are called negation laws. And it says that if you OR P with the negative of itself, you just get a true. And we looked at this expression as an example of tautology earlier. And we have another negation law. If I take P and not P, this is going to give me a contradiction. So don't get confused between negation laws and double negation law. Double negation law simply said if you negate 2 times, you're going to get back the original proposition. But a negation law explores what happens when you look at conjunctions and disjunctions of a proposition with its negated value. Okay, next let us move into the last segment of our video, and that's going to look at some laws that involve implications. And we have discussed some of these laws earlier. We'll just go through this quickly as well. So P implies Q, you know, is equivalent to not P or Q. We discussed this in our implication video. We also know P implies Q is equivalent to its contrapositive, not Q implies not P. There is one that says P or Q is equivalent to not P implies Q. Okay, and this comes as a derivative of this one. You can simply substitute P with not P and get this expression. Okay, let's look at this one. P implies Q and P implies R. This would imply P implies Q and R. So this states that when P happens, Q happens. But R also happens, right? Because P implies Q and R. Therefore, I could say P implies both Q and R. Similarly, let's look at this one. If P implies Q and I have R implies Q. So here's the trick. This is P or R, okay, implies Q. And see why this is different? In this situation, when P happened, Q happened and R also happened. So I can conclude that P implies Q and R. But this is different. This is saying that P is one of the reasons for Q. So Q happens when P happens, but Q also happens when R happens. So we can conclude that Q happens if any of P or R happens. And what happens when I use OR? Let me consider this one. P implies Q or P implies R. So this expression is saying if P happens, Q happens. And this is saying if P happens, R happens. And the OR suggests that both of these might not necessarily be true. Therefore, the best I can conclude is that whenever P happens, one of Q or R will happen. Okay, so P implies Q or R. So the only idea is the AND here translated as an AND, but the OR here would be translated as an OR. Okay, so these are the most important laws. And before closing the video, I just want to do a 1-minute discussion on satisfiability. So I think this will be relevant to us in a theoretical regard. It could be asked of us what a satisfiability problem is and how it is related to propositional logic. And we looked at some form of the satisfiability problem earlier. When we looked at the topic of system consistency verification, we were given a list of propositions and we wanted to make sure that they were not contradicting each other. And satisfiability is also kind of similar in the sense that it looks at, can a problem constraints be satisfied? So let me give you an example that I think many of us can relate to. So let's assume that we are playing a mystery game and we lock ourselves accidentally into a room. Now we realize that in order to go to the next room, we need a key, but we already left the key behind on the last room. And then we realize that at that stage, the problem is not satisfiable. So you choose to reset the level and go back to the last room and hopefully remember to carry the key this time. And by the way, this is one very niche example of the satisfiability problem because it will generally apply in any situation where you want to check that a given set of observations is consistent. So take the Sudoku puzzle for another example. I need to be very careful when designing a Sudoku puzzle because not all configurations of Sudoku are solvable. Therefore, I need to ensure that the satisfiability criteria are met, that the numbers given initially in the puzzle can ensure a valid and unique solution. And we also solved one practical example when we discussed this topic earlier, system consistency verification. So we saw that the system was consistent for 3 propositions, but then we saw that upon adding the 4th proposition, the system was no longer consistent. Okay, so that finishes the discussion for this video and for propositions. In the next video, we'll explore the topics of predicates, quantifiers, and binding variables. I'll see you in the next video. Until then, have a good day and bye.